Or did you pause it?
No, I actually stopped it and restarted it. So yes, you're on the video. Okay, you're about to be immortalized on YouTube. Yeah, so we'll just see what happens, and you know, I'm accustomed to having a bunch of stuff dumped on me at the end of a semester, so, and that wouldn't really bother me in this class because there's only 4 of you. So, okay, so continuing with the heat equation. At the end of this class last time, I derived it, so now I'm going to solve it, or at least one particular heat equation problem. Okay. So if I'm lucky, this will be the last class that's about analytical methods. So that's stage 4. Finally talking about numerical methods, maybe on Wednesday. So we're solving the heat equation. So no coefficient, because I showed you how you could eliminate the coefficient when it's constant. And then we'll have initial data. And the problem will be solved on the entire real line. So no boundary conditions, which is nice because boundary conditions are a pain. And when we have this one-dimensional problem on the entire real line, we call that the Cauchy problem. I have no idea why. Well, I'm sure it's because Cauchy was interested in it, but so what I could do is some problem of interest to me. I could call it the Lambert's problem, and students like yourself, 50 years from now, will have to solve it. So, I mean, if I can't have a research method named after me, maybe I can have a problem named after me. So, okay. I'm sure I could be as dastardly as any of them. Okay, so way I'm going to solve this I'm going to use the Fourier transform. Okay. So, in other words, I'm going to take the inner product of both sides of this PDE with e to the I omega x. Now, so I want to point out the notes that I'm going on, that I have on the site, are really terse because I was lazy in writing them. So it basically says, oh, here's the solution. And it may say a little bit about how you get it, but not a whole lot. I am going through it all here because I don't really like to pull things out of thin air. And there are a lot of tidbits that you're going to see here that I think you might find useful for other problems. Like I always say, a difficult math problem is actually an easier math problem that's being looked at the wrong way. And that doesn't help anyone unless they have some idea of how to change viewpoints. What are some examples of a different perspective on a problem? So you're going to see some of that in what I do today. Okay. So when I say, like we're talking about things you can do to an equation. You're accustomed to doing all kinds of things to an equation, like multiplying both sides by something or adding, subtracting both sides, those kind of operations. So a good thing to add to your repertoire at this level, this being a 700 level PhD class and all, and apologies to you new master students, but is this operation, taking the inner product of both sides of an equation with some function, when the equation itself already has functions in it, because it's that routine an operation. So what does this mean? When it's inner product of functions, you multiply both sides I need to leave space for a reason. We multiply both sides, not by what you're taking the inner product with, but actually its complex conjugate. So that would be e to the minus I omega x. So imaginary parts are negated. And then you integrate. So I mean, you have to know what the inner product is in this case, but we're dealing with the whole real number line. So whatever spatial domain your problem is on, that's what you'll integrate over. So in this case, minus infinity to infinity. So that's what I mean. So when I say take the inner product with this, if it's functions, you multiply by that function, integrate over the appropriate domain. If these were ordinary vectors, you'd be multiplying by the Hermitian transpose of whatever it is. So you transpose and complex conjugate. Okay. So now we have this. So now I want to simplify both sides of that based on properties of the Fourier transform. So here, this is just a Fourier transform of du dt. So I'll have that. So I use hat to indicate the Fourier transform of whatever it is. And then here, the Fourier transform of a derivative with respect to x is just going to be the Fourier transform of the original function times I omega to whatever order derivative. So in this case, it's going to be squared. Okay. Now, the reason why this is very helpful is our PDE becomes a one parameter family of ODEs. So in other words, this PDE we now have separated to several equations, each one of which is simpler to solve. When we do solve it, it'll depend on this parameter, omega. So omega is a parameter in question. Because notice x, our original PDE was in terms of x and t. X is gone now because we took the inner product. And we still have t. Now, for ODE, for a problem involving an ODE to be fully specified, what should the problem include? Besides the ODE itself. What? To ensure that there's a unique solution.
Equal to 0?
What?
Like conditions, like boundary? No.
Oh, well, other kind.
Initial?
Yes, initial condition. So from that, we take the Fourier transform of the PDE's initial condition. So the initial condition is going to be, so u hat of omega 0 is going to be a Fourier transform of this. So that'll just be u naught hat of omega. Okay, and because u naught is assumed to be given. Okay. So now we just need to solve that. Now, actually, that's the easy part. The rest of it's still going to be a pain. So if I go up here and rewrite this, so we have u hat t of omega t. So I omega squared, that's the same as minus omega squared. U hat omega t. And then initial condition. Okay. Now, this kind of ODE we have seen before. Can anyone think what the solution would be? So all we have is your solution is here, its first derivative is here, and this is a constant. So it's like y prime is equal to ky. It's that kind of ODE. So we know, we have seen how to solve it. So the question is,
In this class?
yes, we have, like more than once. So, does anyone remember?
Is y e to the k?
Yes. Okay, so
Or
what would it be?
e to the k?
What goes with the k?
X, y, z.
Well, you're kind of in the ballpark there, but not. Okay, so this is y prime of t equals ky of t.
So t.
Yes. I guess I kind of looked at that one. Yeah, times what?
T? Like the whole thing?
Like this times what completes the solution?
Constant?
Yes. What constant?
C? No.
The initial value.
Um,
Yeah. So yeah, because when t is 0, this becomes 1. You want to have the initial value there.
yes,
Okay. So, in this class, I don't mean just mean this course, but also today in particular, there's going to be a lot of good to know things that I'm putting out there. I put this one out there before. So this is one of the main good to know things. Is because this ODE, as we've already seen in the short period of this course running, keeps coming up.
So what would that be for?
Well, let's go ahead and do that. But to finish my pontificating, whatever you guys can do to drill that into your head, do, because your brain will thank you. And so will I. So if you apply the same idea, you can write down what this is going to be. So you figure, okay, if you're relating this to this, like what do all the different pieces mean? What's your y? What's your prime referred to? What's your k?
Negative W2K, or negative W to the second.
That is your k, yes. So now we have a solution to this one. I want to write down the solution to this. Yeah, 'cause this is certainly playing the role of a y, or y of t. It just happens to have its parameter omega, but. So you can write something down that's going to mirror this. Yes, good start. All right, keep going. Anybody?
Negative W squared.
Yes.
T.
T.
I love this. Each person contributing piece. Finish it off.
Not.
Yes. All right, that's teamwork. Okay. All right, gold stars for everybody. Okay. All right. So what this is not the solution of a PDE though. It's the Fourier transform of the solution of a PDE. So we could say that.
Wait, so that's the Fourier transform
Of
of the
the
solution?
Yes. In other words, the way I could write it is fancy f of u of xt, where this refers to Fourier transform. So I could then say that u of xt, which is what I'm really after, is the inverse Fourier transform of this. Still going. Please tell me you're still recording. Blur. Yes, it's still going. Okay. Now I can give you a definition. So just as this was a Fourier transform, the inverse can be written also as an integral. You just have to have a 1 over 2 pi up front, and then e to the plus I omega x. And then all this would go in here. Okay. Yeah, and then d omega instead of dx, because the output of this is supposed to be a function of x and t. So we have that, except that doesn't really help you if you have no idea how to evaluate an integral. So now I need to discuss that. It's actually a fairly long journey to the solution, and we've just finished the first part, so strap in. All right. Now, there's one property of Fourier transforms that is going to help us, because right now our Fourier transform is a product of two Fourier transforms. It would be nice if we could somehow use the inverse transform of these two items individually to figure out the Fourier transform of them multiplied together. And there actually is a property that can help us with that. Because this is just a Fourier transform of the initial condition. Now, the inverse transform of that, you guys don't know yet, but I'm going to show you. So there's actually a few pieces I have to work out here. Okay. So first, how to get the inverse Fourier transform of a product. So we have two functions of omega multiplied together, and say if you know how to inverse transform them individually, how could you inverse transform a product? So the idea is these individual transforms are known. So where actually I put hats on these, where the original functions are known. Okay. So what I do is I say the inverse transform of f hats, g hats. So I use the definition that I wrote down there. So it'll be 1 over 2 pi integral e to the I omega x f hat of omega g hat of omega d omega. Okay. Now the next thing I'm going to use is some trickery. Because I can pick one of these functions, f hat or g hat, and write it in terms of the corresponding function of x. So I'm going to use the definition of the Fourier transform, and then I could pick either one. I'm going to use it on f. So I still have this, and I still have this. But now I'm going to rewrite this in terms of the Fourier transform. So I still have this d omega on the outside. And I'm going to fill in the definition of f hat of omega in there. And I had it written on the board earlier, but I erased it. So let's see it. Integral minus infinity to infinity e to the minus I omega. Now here, I cannot use x. So I already have x here. This whole expression is a function of x. So I need to pick a different letter. I'll just use y. E to the minus I omega y f of, oh, I totally goofed. Well, it's fine. I guess really I can pick either one, f or g. Okay, so this is the definition of Fourier transform. Now, there are all kinds of manipulations like this where I'm trying to figure out one integral, and I do that by introducing another, so it makes it seem like I'm going the wrong way, because I'm trying to get rid of all the integrals. And what you do is you switch the integrals. You switch the order of integration. So that's just one of those techniques you should have in your bag of tricks. You're trying to work out some like double integral, you swap the integrals. Well, sometimes you have expressions following a double summation, and you make something simplified by switching your summation. Just switch stuff. It's something that helps a lot. So that's my wisdom of the day.
So you switch the order of integration to do what? To
see what you can simplify. Because what I'm going to do is I'm going to have an integral with respect to y on the outside and omega on the inside. So I go ahead and do that. I go from minus infinity to infinity. So I'll have dy out here. So the thing is, I can have the integral with respect to omega inside now. So that means that anything that is independent of omega, I can put out here. What in here is independent of omega? Not much, but what is? F. So I'll go ahead and fill in F. Okay. So now everything else depends on omega. So let's put that here. So I have minus infinity, and okay, I have these two exponentials, I omega, so I'll have d omega. I have e to the omega x and e to the minus I omega y. So I can combine them, e to the I omega x minus y. And then g hat of omega. And although I can put it anywhere, I'm going to get rid of 1 over 2 pi out here. I'm going to put it in here. Okay.
So when you say you're switching the order of integration, you just d omega and dy.
Yeah, that's all I'm
okay.
doing.
Okay.
Yeah, I mean, just put things where you're allowed to put them.
Right.
Yeah. Okay. This is, you recognize this as an inverse Fourier transform because we have 1 over 2 pi, integral from minus infinity, d omega, some function of omega. You have an exponential of I omega something. It's just that if you look over here where I previously wrote the inverse Fourier transform, if you, again, all of this is pattern matching. match this to this. Like here I have some specific function of omega. Here I have something that's general. Here I have e to the I omega x. Here I have e to the I omega x minus y. But this was used to get the Fourier transform, inverse Fourier transform, and I get a function of x. So I have x here, x here. So if I go ahead and write this again, first part of this doesn't change. So this is the inverse Fourier transform of what?
G X T. No. Of like e to the negative. Wait, I'm looking back.
Right.
It's whatever is in the brackets of like the inverse where you like e to the negative omega squared t.
Yeah. So like right. So for instance, this almost matches the general inverse Fourier transform, but in the general definition, I only have e to the I omega x. And then whatever it is you're inverse transforming goes here. So, okay, I'm still going to have my dy here. So like here, this is u hat of omega t. We apply the inverse transform and we get u xt. So the omega goes to an x, and the hat goes away because we've untransformed it.
So do we need to like separate an e like full?
Well, okay, so what is the function that we're going to have here? G, yes. Because we have g hat, we're inverse transforming it, it brings us back to g. But now we have to look at what else is different between this and that.
Well,
X minus Y?
Yeah, but x minus y is only specifying the evaluation point. So in other words, you could have anything here, e to the I omega crap, and therefore you plug crap into the function, whatever it may be. And that's it. That's the answer right there. That the inverse transform of a product of known transforms is this, which is written as f fancy asterisk g, which is a function of x, because this is an integral with respect to y. If you were to evaluate this integral, your output would be a function of only x. And this is the convolution of f and g. So that's just the definition of it right there. So the inverse transform of a product is the convolution of the inverse transforms. Okay. The inverse transform of a product is the convolution of the inverse transforms. Of the inverse transforms. Yeah, and here we have f inverse hat of f hat g hat is f convolution g. So, what does that give me, though, for a heat equation? Only a little tiny bit. It tells me that if I can get the inverse transform of that and the inverse transform of that, then I'm done, because I just take the convolution and that's it. Now, this part is no problem. I do know the inverse transform of that. It's just u naught of x. I do not know the inverse transform of that. So now I got to work that out. So we're getting there, I swear. Maybe by the end of class we'll have it. Okay. So there's questions about what happened here. All right.
What were you saying earlier that like you could have done G hat and not done F?
Oh, right.
Would that change anything? Or?
Actually, yeah, I've actually meant to write that down. So I can write this convolution in two different ways.
Mm-hmm.
It's also equal to, if I just switch the roles of f and g, I can say g of y, f of x minus y, dy. So in other words, this convolution is commutative. So f star g is the same as g star f. And because I want this to be a function of x minus y, that's why I realized, oh, I goofed, but it doesn't really matter. Any other question? All right. So the next thing I'd focus on is, to be order to apply this, I need the inverse transform of that. So what is the inverse transform of e to the minus omega squared t? Okay. So now a logical place to start when you have no idea what to do. Start with definition. Now, it seems like a dual kind of thing, but students don't seem to have that as a reflex yet. So, not sure what to do. Well, so going to start with definition anyway. Okay, so it'd be 1 2 pi, integral minus infinity to infinity. So I'll have e to the I omega x, e to the minus omega squared t, d omega. So I need to try to evaluate this integral somehow.
Oh, you don't have to have you.
Oh, yeah, because I'm right. I'm only doing this. Okay, so to reiterate, if I have this, and I already have the inverse transform of u naught hat by itself, because that's just u naught,
That's
then I do the convolution.
G, or is that F? Which
I really want to play the role of f.
okay.
But yeah.
So you know that's F, G.
Oh, wait. Sorry. I really want to play the role of g. Because I want to plug x minus y into my result. But we're going to deal with that later. Okay. All right. We're focusing on only that. Okay. Because the situation I'm in right now, I want to do this, and I know one of these. I don't know the other. Okay, so we have some good old-fashioned calculus to do here. Well, actually it's more algebra than calculus. First I'm going to put these in one exponent, e to the minus omega squared t plus I omega x. I'll just put it into one exponent. Now, the next thing I'm going to do is, there is going to be something I could do if I have an integral involving just a variable of integration, like e to something like this, where the exponent is a perfect square. But this throws it off. If I can make this into a perfect square, that's something I can do something with. So what do I need to do with that? Complete the square. And this is going to kind of relate to...
Yeah, funky eye stuff does.
Okay, but it turns out it doesn't really affect how you proceed. It just makes it messier because it's there.
Yeah.
So completing a square on this. All right, so I need to pull out a minus t just to make the coefficient of this 1. So now I have omega squared minus I omega x over t. Okay. I have to be really careful with my algebra because when I was working this out on paper, I screwed it up and had to fix it. So hopefully I won't do it again. So completing the square on this, so I'm going to have omega minus I x over 2t squared, because that's going to give me omega squared, and then minus twice this times omega, so I omega x over t. So then I have no constant term out here, so I need to make sure to, like whatever, I have to square this term here, which is going to give me minus x squared over 4t squared, because minus I squared is minus 1. So whatever I have here, when I square this term, I have to subtract it off. So that means I need to put plus x squared over 4t squared. And that's still in these square brackets. All right, so that is the square completed form of what I have in here. Yeah, pretty ugly. Question? That's assuming you got it right. Questions? Check my algebra. Actually, probably could use that. Actually, I'm going to check it right now. So, omega squared, okay, so minus I x omega 2t, okay. Double that. All right. And then, okay. Now, so the next thing I'm going to do is do some distributing here. So I have e to the minus t omega minus I x over 2t squared. And then I have e to the, I have a minus t here, and then a t squared in the denominator. So that's going to give me e to the minus x squared over 4t d omega.
T squared.
No, because I have a t squared down here, but times t.
Oh, yeah.
Yeah. All right. Although something is not entirely agreeing with my notes, what did I do? Oh, I see what I did. Ugh. Okay. All right. So my notes are wrong from this point, so I can't use them. But I believe this is right. So let's just see what happens. All right. Now, one thing that helps now is this part here. The reason why I wrote separately, it's not dependent on omega. It's a constant. I can pull it out. So I'm going to go back over here. Alright, so now I have e to the minus x squared over 4t. Then I have 1 over 2 pi e to the minus t omega minus ix over 2t squared d omega. Okay. So, all right. So now what I'm going to do is, to get a handle on the integral that's left, I'm going to make a substitution. And the goal is, I want this to boil down to an integral of e to the minus u squared for some u. So in other words, I want my exponent to be minus a perfect square, which it almost is, except we have that t hanging out there. So what you can do is, I'm going to match this, what I want, to what I have, and that'll tell me what u is. And I'm going to make a u substitution. So good old Cal 2. So if I want this exponential to become this exponential, what should u be? Well, we don't need it yet. It's just making this u squared. So what should I set u equal to make that work?
I don't know to the t.
Well, if I shown you what u squared is.
Did you do that divided by t? Like the inside of the parentheses?
Oh, sorry, what? Okay.
Is it just going to be like omega minus ix over 2t times the square root?
Square root of
omega
t, yeah.
Or,
It's actually the square root of this whole thing.
Okay.
So that means square root of t also.
Mm-hmm.
Yeah. So that's another thing that I like to do often in these problems. Whatever you need,
but,
just force it to be that.
but it's negative, so.
I have a minus here also.
Oh, okay.
Yeah, otherwise I would need an I.
Right.
But, okay, so then that already is a perfect square, so I just remove the square. So that's it. That's all I need. Yeah. So you just say these things are equal, and then clean up a mess. You can see what a mess it is. Works though. Okay, now for my u substitution, do du is equal to this. Now this, omega is the old variable, so I need a derivative of this with respect to omega, but that's going to be square root of t. So that's going to tell me what I need to do to transform the integral. So now, all right, so I still have a 1 over 2 pi. And because of this, it's d omega I have to replace. So d omega is 1 over square root of t du. So now I have a factor of 1 over square root of t that I can just pull out. Normally with a substitution, you also got to change the limits. But the original limits are minus infinity to infinity. And this is just a scaling and shifting of omega. So I'm scaling and shifting the entire real line, which is still the entire real line. So yeah, I am changing the limits, but the limits don't actually change. But I'm checking that. Minus infinity to infinity. And now the integrand transforms into what I want. Let's set it up that way, minus u squared, and then du. Okay. So we're almost there. I've boiled my original integral down to one that appears to be a whole lot simpler. Except I don't about that integral. This is a Gaussian function. Or the simplest form of a Gaussian function. It's been proven that it does not have any antiderivative that can be expressed in terms of elementary functions. Like if I had e to the minus u without the square, you could do that, or other variations. But that one, you can do all the cal 2 you want. You'll never get it because it's been proven that you can't. That's kind of weird. To prove a problem can't be solved. And I don't know. I haven't seen the proof, but it's got to be pretty interesting. Fortunately, I do have a way of working out this integral. At least I can't produce an antiderivative, but this definite integral from minus infinity to infinity, that one I can do. And for that, I will use Cal 4. And you two who took Cal 4 from me actually saw me do this on the first day of class. And you're probably like, so, and I'll try to keep it brief because it took a whole class period. So I don't want that to happen now. So how do you do this? It turns out that it actually helps to try to do two of them all at once. So if I have the integral, so this is just separated from all this. Suppose I have e to the minus x squared dx times e to minus y squared dy multiplied together. It's actually easier to do the product than to try to do one individually, because I can move one integral inside the other and give myself a double integral. Now, why would that help me? Because now I'm going to switch to polar coordinates. And you go, how's that going to make anything better? But actually, it makes things way better. So, does anyone know what x squared plus y squared is in polar coordinates, r and theta? Okay.
Is that sine and cosine?
What?
So,
Well, polar coordinates is x equals r cosine theta, and y equals r sine theta. So that's how you go from polar to Cartesian. So actually, if you went ahead and worked out what x squared plus y squared is and used whatever trig identity you know,
would you have to, okay.
Just R.
yes, it's r squared. Yeah, r squared cosine squared plus r squared sine squared. Sine squared plus cosine squared is 1. The only trig identity that I can count on everybody to know. And yeah, so it's r squared. Okay, now the limits, we're integrating over the entire R2. Now in polar coordinates, that would mean that theta, the angle, goes all the way around, 0 to 2 pi. R goes from 0 to infinity. So that covers the whole plane, xy plane. So I have e to the minus r squared dr d theta, but I'm missing one thing. So you may remember from your multivariable calc that when you make a change of variable like this, you have to include another factor. It's called a Jacobian. And there's a particularly simple factor that you have to remember to include here when you switch to polar coordinates. What does it have to multiply here to make this right? Yes. So dx dy becomes r dr d theta. And so it seems like I have an integral that's not much different than before, but this factor r makes all the difference in the world. So now I can do a u substitution. U is equal to minus r squared. Actually, I don't need the minus. R squared is enough. And then I have du would be 2r dr. So this r dr gets swallowed up, and we get du over 2. So now there's nothing in here that depends on theta. So the integral with respect to theta, I could just do. So I could write it this way. Integral from 0 to 2 pi of 1 d theta, just because the integrand doesn't depend on theta. And then I have 1/2 integral from 0 to infinity of e to the minus u squared. Oh, no, e to the minus u du. Okay. Now, so that's the integral I can actually do. So with this integral, it's going to be, you're integrating 1. So it's just the difference of the limits. It's going to be 2 pi. This, I'm going to have the e to the minus e to the minus u with limits 0 and infinity. Well, e to the minus infinity is 0. So you plug in the lower limit.
Is it negative e?
Yes,
Okay.
because of a minus here.
Okay.
Yeah. You plug in the lower limit and you get minus 1, but it's minus a minus 1 because it's the lower limit. So ultimately, what do you get when you simplify everything? Pi. Questions about how that happened? I know I kind of glossed over the last steps, but. All right. But I had 2 of them multiplied together and got pi. Here I only have 1, so I got to take square root. So this whole thing here is the square root of pi. So sorry, this is placed inconveniently. So now I can fill that in, and ultimately what I get is 1 over square root of 4 pi t. I moved the 2 under the radical sign, and therefore becomes a 4. Just have to make the expression a little nicer. And then I have e to the minus x squared over 4t. So that is the inverse Fourier transform of e to the minus omega squared t. Finally. Okay. Any questions there? All right, so now it's just a hop, skip, and a jump to the end. Actually, we've done the hop and the skip already. So, the final jump to our solution of the dang heat equation that we started with. Okay, so what we had before was that the Fourier transform of a solution is e to the minus omega squared t u naught hat of omega. Therefore, u of xt is the inverse transform of that. Okay. But that is going to be the convolution of the inverse transforms of these things individually. So it's be the convolution of, so the inverse transform of this was just worked out, so that's going to be 1 over square root of 4 pi t e to the minus x squared over 4t. Convolution with the inverse transform of that, which is just u naught of x. So now I have the solution expressed in convolution form, which I can then write as an integral u naught of y times this. Well, the constant factor I'll just move outside. So I have e to the minus, and instead of x, because it's convolution, I'll have x minus y squared over 4t dy. So that is the solution. Seems almost anticlimactic. Or climactic. So one thing's kind of weird here is, as t goes to 0, you have a problem down here, just blowing up. But at the same time, because it's going to 0 here in the denominator, your exponent is becoming negative infinite, like faster. So this becoming large is offset quite a bit by this becoming so small. So it's still well defined even as t goes to 0. Now, so I want to explain, like, how would you interpret this, like, physically? Whenever you take the convolution of some function with a Gaussian, it has the effect of smoothing that function out. Because really, you think of what this is doing is this integral. It's like taking a weighted average of values of u naught, where the value that plays the largest role is when this exponent is 0, so at x. So values away from x are given lesser and lesser weight because this exponential is decaying as you move away from x, as y moves away from x. So that's why so that's how there's the effect of smoothing u naught of y. So if u naught of y is your initial temperature profile, that's your initial condition, and then you solve a heat equation, and what you find as time progresses is that temperature profile smooths out to a constant. And that's what this actually accomplishes by this convolution. The larger t is, the more this, so because the Gaussian function, behaves like that. That's what a Gaussian function graph looks like, bell curve. It literally is a bell curve. As t increases, that bell widens. And that's what causes the temperature profile to smooth out. Well, that was fun. Okay. Now, so that was just for a simplest form of heat equation, ut equals uxx. Now, I want to give a couple of generalizations where I'm not going to work through all the details again because we simply don't have that much time, but really the most interesting details have already been included here. Now, what I showed you there was a solution in one dimension. So, in higher space dimensions, ut is a Laplacian of u in however many dimensions you have. And same kind of initial condition where x is now a vector, a vector valued quantity. So the solution has a similar form. It just has to be generalized to higher space dimension. So it's going to be an integral, still have this factor, 4 pi t, but instead of the square root, it's to be n over 2 power. And that just comes from a definition of the n-dimensional Fourier transform. And then I have integral over all of Rn. I still have u naught of y. And then I have the same kind of Gaussian function, e to the minus magnitude of x minus y. Over 4t. Okay. Where this is Euclidean length, so that's the square of the sum of squares. Okay. So it's a relatively straightforward generalization of a solution I just derived to n dimensions. And then a further generalization. What if I add a source term on the right side? So in other words, instead of just having a initial temperature profile and seeing what happens over time, which normally just the heat energy just diffuses throughout space, if you have some term that's indicating a heat source, so heat could be added to the system, so then it may not smooth out quite so much, maybe not at all. It turns out there's this relatively easy way to write down the solution of this problem in terms of the solution of this one. So, now in this case, I'm going to give an initial condition of 0, to simplify matters. So I have u of xt is the integral from 0 to t. Okay, that's where to write this. Really, it's going to be something along these lines. But what I have to change is quite interesting. Okay, so I'm going to have this factor, but instead of t, I can't use t here. My limit of integration is t. So here I have to use a different letter, so I'm using s. So one thing is, instead of t throughout here, I'm going to have t minus s. Integral over Rn. And then instead of the initial data, I'm actually going to have my source term evaluated at time s. And then I'll have this exponential factor. Over 4, instead of t, again, I'll have t minus s. D. Oh, sorry, that should be y. And this should also be y. Okay. So that's the solution to this inhomogeneous heat equation that has a source term to it, if there was initial data, I would just add this on. Okay. Now, I'm going to describe in words what I've just put here. So this is a solution of the homogeneous heat equation with initial data is your source term evaluated at some time s, but the solution is evaluated at time t minus s. So, to interpret that, so think this way. At time 0, we have f of x0, that external source, the heat source, introduced. And that gets evolved to time t, because s is 0 in this case. Now, at a later time, like, so at a later time, this is still being introduced. But I'm evaluating my solution at t. So let's look, like, for example, suppose I'm looking at what happens at time t over 2. So whatever this value is introduced at time t over 2. And from t over 2, I'm evaluating my solution at t, so that part is evolved t over 2. So at every single instant between 0 and t, I have this introduced into my solution and evolved from where it is introduced up until t. So, because what we see here is the time that the heat energy is introduced, which is s, plus the time over which it's evolved, t minus s, adds up to t, which is where I'm evaluating the solution. All right. So this solution formula is called Duhamel's principle. So it's a general way to write down a solution of an inhomogeneous PDE in terms of the solution formula for a homogeneous PDE. So at every instant, starting from 0, the source term is contributing something to the solution. The contribution at each instant is evolved up to whatever time you're evaluating a solution. I give you an idea of where this comes from ODEs. It's easier to see. And really good, I imagine it's where how Duhamel's principle can be derived in the first place. Suppose you have this system of ODEs, where A is just some constant matrix. And you have initial condition. Actually, this is similar to the ODE I wrote on the board way back earlier today. So what would the solution be? It's the same idea. Yes? Oh, I don't have the negatives time. Okay. Yes.
T.
Yes.
Why not?
Yes. Okay. All right. Well, at least this side of a room contributed. Okay, that's the homogeneous system of ODEs. So now if I have y prime equals ay plus f of t, and I still have the same initial condition, then I can say that y of t is equal to, so I still have this term out front, plus, well, so what follows is it accounts for the source term here. Integral from 0 to t, and I'll have e to the a t minus s times f of s ds. Okay. So again, the time at which the source term is evaluated plus the length of time over which it's evolved adds up to t every time. So Duhamel's principle is really just this applied to PDEs. I should mention that how you get from here to, how you get from here to here is from this ODE being separable. How you get from here to here deals with something else you also learn in your first ODE class, like Math 285. First order linear equations that you solve using an integrating factor. Does that ring a bell to anybody? Okay, so so that's where this integral comes from. But I won't do that here because you've suffered enough. Okay. Yeah, one thing I'm not interested enough to go into. I mentioned last time Laplace's equation, harmonic functions satisfy maximum principal solutions of the heat equation, also satisfy a certain maximum principle, which also can be used to establish uniqueness of solutions. But if I remember to spend my time doing this. But that's in the notes. Okay. Let's see, I have 9 minutes left. And I was still supposed to cover the wave equation, but I cannot do that in 9 minutes. Because it's all this. Well, I'd skip some of it, but yeah. Okay. Yeah, this is a natural stopping point, I think. So I'll do that wave equation stuff on Wednesday. So then next week, finally numerical methods. I got to make sure to really have good videos for that. Not everybody will be here, but okay.